Any questions? All right, so we're in the middle of section 5.4, which is the last section for Calc 1, fundamental theorem of calculus. Like I said on Monday, we're probably going to get through this somewhere toward the tail end of today. So if you have any questions about the final or where we're going or anything at all, we'll have time to talk about that. Hopefully sometime today and the entirety of Friday. All right, so I'm going to talk about this fundamental theorem of calculus, and the big idea here is that these seemingly disjoint ideas of derivatives and integrals are actually basically two sides of the same coin. They're very closely related. All right. So based on what we've done, how would I find the derivative of this thing here? Does this derivative exist, first of all? How do you know the derivative exists? The denominator cannot be zero, so that's very important. So why specifically are we interested in the fact that the denominator cannot be zero? Not only defined, we got to go a little stronger. So yes, it's defined. That's important. Yes, differential. We actually don't need to go that far. So, for example, I'm not saying this function does look like this, but what if I did have a function that, from 0 to some value x, the function kind of looked like this? If that graph represented that function that I'm showing you, I would not be able to say the derivative. Why not? What's not true about the graph function that needs to be? Right. So I need this to be true. So we'll call this thing right here f of t. So one check mark is this: f is continuous. So it's a rational. Well, I mean, the numerator is a polynomial. Those are continuous absolutely everywhere. The denominator is a radical function, which, as we've identified, as Zach pointed out, that can never be zero. So this thing is going to be well-defined and continuous everywhere. So because of that, can we say, or we can say that this derivative exists? Can we say what the derivative is exactly? Exactly like that? Right. So basically it would just be this: x cubed plus x minus 1 over the square root of x squared plus 7. And it seems kind of mysterious, like I'm just changing symbols, but let's really look at what's going on here. If I have the integral, and let's just keep the limits the same, from 0 to x of some function t. So even though I'm going to go ahead and tell you this for free, even though maybe I've given you enough to know this, but this function f of t is differentiable. It's differentiable everywhere. So specifically from 0 to some number bigger than 0. Because that function is differentiable, then I can say this about that function, right? F of x minus f of 0 is equal to capital F of x minus capital F of 0. And just a reminder, since we're going to be using it a lot, this theorem, how are the functions lowercase f and capital F? Right, so lowercase f is the derivative of capital F. Or going the other way, capital F is the antiderivative of lowercase f. So if that's what this function is equal to, then I can say this: a of x is equal to f of x minus f of 0. So when I take a derivative, I'm going to get this. A prime of x is equal to capital F prime of x minus, what's the derivative of f of 0? Yeah, that's a constant, so that goes to 0. So all we get here then is capital F prime of x, which by definition is just f of x. So, I mean, there's, mechanically, you can just, from an outside observer, there's actually more to it than that. Any questions so far? I think this is quite a bit like what we've done before. By the way, do we know what the antiderivative of this f of t is? I don't think I've given you enough weapons to get it. F of t is the whole thing, so yeah. Yeah, f of t is equal to t cubed plus t minus 1 over the radical t squared plus 7, which, though it exists, that's not an easy thing to get our hands on. Any questions here? Yeah. All right, how about this one here? The derivative of this integral from 1 to x to the 4th secant of t dt. Is there any difference here from the things we've done? The upper bound is not simply x, right? So this is kind of a new thing. Let's talk about, all the layers of what's going into this function are. So my base, like my fundamental, my foundational variable here is t. What am I doing to that t? Let's just kind of follow the journey of this symbol. What's then happening to t? No, there's quite a bit of stuff that's going to happen between here and there. And I think based on what we've done, the temptations to look this, all right, the answer to this derivative is secant of x to the 4th, which is not quite that simple. So if I follow, now let's think of it this way. Let's call f of x is equal to this integral from 1 to x to the 4th of secant t dt. In fact, let's not look at t as the base variable, let's look at x. Sorry, what was your question, Saul? So hold that thought, see if what we end up with kind of agrees with the way you're saying it. So now that we're looking at, if we look at x as kind of the fundamental variable that's governing this, what's the first thing that happens to x here? Right, it is raised to the 4th. And what comes out of that is x to the 4th. Then what am I doing with that x to the 4th? I'm not putting it into the secant. Not directly. Think about what an integral does. So yeah, that's exactly it. Based on some things I've seen some of you do, and from just my experience with other classes, let me put a counter example over here. I've seen this a lot. So let's say, for example, I want to integrate from 1 to 4 of x dx. Actually, let's make it x squared dx. Especially early on, you'll see a lot of things like this. Okay, well, that's x squared from 1 to 4. I'm just going to take 4 squared minus 1 squared. You don't have to admit it to us, but I'm sure that a lot of you have fallen into this trap before. What's wrong with this? What did I not do? I didn't take the antiderivative. So because of that, I am not just taking that x to the 4th and plugging in a secant. What I'm actually doing, and I think it's probably more helpful if we just take it all at once, is I am integrating. I am doing an integral from 1 to x to the 4th of secant t dt. So let's just stop there for a second. Are we okay with the fact that those are to raise up to the 4th power, and then we're going to integrate secant with that fixed limit fixed lower limit 1, the variable upper limit x to the 4th. All right, so now, if we're okay with that, we can just handle chain rule with this the way we've always done. So what would the derivative of this integral be with respect to x to the 4th? Well, actually, that step right there, maybe we should do what we've done in the past is this. If f of x is equal to this thing, let's say g of x is equal to x to the 4th, and h of x is equal to the integral from 1 to x of secant t dt. And then from there, can I say that f of x is equal to some composition of g and h? Are we happy with that? So all I'm really doing right now, I'm basically I'm processing this function through smaller functions and composing them together. All right, from there, think about the way we've done chain rule with things that don't have integrals in them. How do I handle this derivative now? So let's go from, yes, since we're multiplying, it doesn't matter which order we go, but let's go from the very outside in. Sebastian, do you have a question? Right, and that's a step that I kind of missed. What is the derivative of h here? Secant x. And with the derivative of g, that's something we've been doing for months now. What's that derivative? 4x cubed. So then from there, if we want to build up the derivative of f, we need h prime of g of x, right? Times g prime of x. So h prime of x is secant of x, but I want to evaluate it at g of x. So that'll be secant of x to the 4th. So maybe the thing you were tempted to do all along, I mean, that was probably it. That's just mechanically, it looks like we just plug in whatever that upper limit is for our variable t and we're home. But then we have to multiply that by 4x cubed. Question? How is the derivative? I'm going to remind you of that over here in the margin. So if f is continuous, then we get all this for free. I don't remember what we called the function. Might have been a, but a of x, this right here, from a to x of f of t dt. This function a is an antiderivative of f. And looking back on the video last night and the notes, I think I was probably not clear enough about this. But the importance of the fundamental theorem of calculus is this. All right, so if f is continuous on some interval, then that function a, which I've just described that way, is related to f in a very specific way. A is an antiderivative of f. Or another way you can think of it is this: a prime of x is equal to f of x. That look at it right there is exactly why the derivative of h is what it is. Any more questions on that? I don't want to gloss too fast, but that's a very important thing. So again, the fundamental theorem of calculus, basically the thing that joins these two schools together of derivatives and integrals is the fact that they are related in this inverse way. Any other questions here? All right. So last thing I want to talk about is average value of a function. So let's start small, something that I know you could all do and something you probably just do in your head without thinking about it too much. Is how do you find the average value of a set of numbers? Right, something we can all do, right? So yeah, if I had 100 numbers and you wanted to find the average of them, you would add them all together, divide by 100, and you're done, right? So we're going to try to apply that idea to integrals. So it's really easy when you have some number of numbers. You can just add them all together and divide them by whatever that number is. How can you do that if you have infinitely many numbers? That's basically what you have when you have an integral. You have infinitely many values you're looking at. So I have a function here, and I have that horizontal line there, which I am saying is the average value of that function, that curve over some span of that variable t. So I'm looking at a continuous function. How do you think I'd find the average value in this case? I can't just add a bunch of things up and divide. I'll never be done. So how can we find the average value in this case? The area above and below what? I don't think. Are you talking about the area, this area here versus this area here? Oh, the blue line. So yes, if we are saying, so I am telling you for free, this blue line here is the average value of this function. So what I'm hearing is that because of that, this area here, which I'll call area 1, and this area 2, or area here I'll call area 2, if that truly is the average of those two, if that blue line really is the average of this black curve, does it make sense? So that's a good first step. If we can think about this in terms of area, is there a way we can find this average value exactly? Maybe if we look at an example here. Actually, no, I'm going straight into the definition. Let's keep building it up. What if let's use a function we can actually give some definition to. Let's look at the interval from 0 to 10 of the function f of x equals x squared. Could we find the average value of this function of that interval? How would we do that? Can someone describe what their idea would be for how to find that average value? But, so you're taking a finite number of x values. And you could take more and more, and that would give you better and better guesses, right? Is there a way to get that exactly? Yes, there is a way to get that exactly. So, and let's think back to how would I find the areas of these? How would I find this area over this area? So can I use this tool, this process of integration to get at what the average value of the function might be? Specifically, this function from 0 to 10 for x squared. Is there a way for me to dial in with this? So could we find this area, by the way? How would I do that? I'm going to go from 0 to 10 of what? X squared dx. That would give us 1/3 of x cubed, evaluated from 10 to 0, and we'd get 1/3 of 100, 1/3 of 1,000. So that's the area, right? So basically to average that, then what would I do? I mean, I had an infinite number of x values. It's kind of hard to think about that, but if I want to get so my total area is 1,000 over 3, and I think you said this, Tal, how would I get to the average? Divided by the length of the interval. So yeah, if you divide that by 10, that'll give you this average, which is 100 over 3. Sebastian. Yeah, so basically we found the total area, right? And it kind of, I think, I found the total area. That area over whatever the x interval is. Whatever the length of the interval. I'll give you a simpler example here. What if I'm integrating on a straight line from 0 to 10 of the function, pretty obvious here. What is the average value of this function? 2. So what's the area going to be if I were to integrate this? That'd be 20, right? And if I divide that by the full length of 10, I get the average value the average value of 2, which we could kind of see it plainly in that one. Any questions there before I put some formal definition behind this? AVG? Average, yeah.
Oh.
G now, I don't know what it was before.
I think.
No. So let's define this a little more tightly. So if you have some integrable function, which everything I just showed you was integrable, if you have some function whose integral exists on the interval AB, then your average value of f is given by this thing here, which is essentially what we did. This part right here, graphically speaking, what is that integral going to give you? Yeah, that gives you the area under the curve, right? This 1 over b minus a, what is that doing? Yeah, you're dividing by the length of the interval or multiplying by its reciprocal, same idea. My fault. Function is integrable on some interval that has an average. Any questions here? All right. All right. So we've talked about mean value theorem for derivatives in the past. There's also one for integrals. So if f is continuous, that means if the integral exists, that means there's an average value of that interval. And if there's an average value of that interval, it means that there must be some value inside that interval. Then when you plug it in, so let me try to illustrate this a little bit. If I had just have some function here from A to B, this right here will be my f average. No matter what your function looks like, no matter what your average is, there has to be some place where the function is equal to its own average. All right, let's go ahead and do a couple of these. Oh, sorry. Can everyone see that, or should I do some erasing? What's the difference between these two equations? Yeah, I mean, all of them, it's just rearranging. They really didn't say. My b minus a, I get the one on the bottom. All right. So I want to find the average value of this function, 1 plus x squared on this interval. So this is our first one. Let's draw a picture to illustrate what this looks like. -1 to 2. Uh, 1 plus x squared. All right, so here's our function. There's our interval. Shown in the area. I want to find the average value of the function. So how should we get started? Find the integral. So what are my limits? I'm going to go from -1 to 2. I'm integrating 1 plus x squared dx. All right, so that's a good place to get started. How do I evaluate that integral? Oh, what is the antiderivative? X plus x cubed. Evaluated from -1 to 2. And I get 2 plus 8/3 minus -1 minus 1/3. And that comes out to be what? I believe 6. All right, so what does that 6 represent? That's the full area, right? All right, so now what do I want to do with that 6? Right, so to get the F average, I want to take 1 over b minus a, so 2 minus -1, times the integral from 2 to -1 of f of x dx, which is equal to 1/3 of 6, which is 2. So this area that I draw, hopefully this makes sense, that this area right here so that rectangular area and that curved area should be the same, right? And it would be if I drew to the right height. So the average value is 2. Any questions about how we got the average value there? All right, now I want to find the value on that interval that satisfies the mean value theorem. So basically what I'm looking for is over this interval, where is the function equal to its own average? Got to vote for 1, where else? Should be -1, right? So if I drew that graph correctly, that should make sense, right? Or did you calculate that? Okay, so let's make sure that we can calculate to get to find out that we agree. So what equation should I be solving then? Yeah, so I'm taking my function. So basically what I'm looking for is this. I want f average to equal f of x. So where does 2 equal 1 plus x squared? X squared equals 1. That happens at plus or minus 1. Do I care about both those x values? Does there have to be multiple values when that happens? No. How many do there have to be? There has to be at least 1. Maybe. All right. Anything else? All right. That was it. All right. So we are through all of the new stuff I have for you. What if I don't want me to be on screen there? All right. So I have your third test to get back to you. You want to do that now, or you want to do it before y'all leave? No, it's fine. Okay. Now at least. I'll pass those back and then we'll talk about. On Friday. Hoffman? Yeah. No. No. Graded. I didn't get back to them. I still have it. If you want to ask me about All right, so the final exam. Do we know? Seven ten. Why do you? It was my choice. No, it wasn't my choice. I wouldn't do that. So, unfortunately, these big coordinated courses, everyone who's taken Math 265 is taking it at the same time, and they didn't want it to disrupt the other finals you have, which happened during sane hours. So, 7:10 p.m. I think you'd rather have PM than AM. Yeah, PM. 7:10 to 9:10.
Yeah.
I think I commute pretty far away too, about the same distance, but yeah. So that is what it is. I can't do anything about that. So 7:10 to 9 p.m. Where is it? It's two floors directly above our heads. So room 308, December 9th. I'll remind you again. I'll definitely visit the people who aren't here, but yeah, don't show the room on Thursday night. People will take in this time, but it won't be. 308. What else? The format will be like you've come to expect, mostly free response, some multiple choice. It'll be quite a bit longer than what you're used to. It's 2 hours long. What else? You can bring a scratch paper, but I doubt you'll need it. Pencil, calculator. What's that? Yeah. It's comprehensive. So yeah, if we've gone over it before, if it's been on a test, quiz, or homework before, it's fair game. Oh, if you have not voted for when you'd like or when you could attend a review session, please do so. I'll make a decision there soon, but unless things really change, I think it's going to be on. I think I'm going to have at least one on Monday night, and I'll probably have time to do a second one, but I'll definitely at least do one. Any questions about what the final's going to look like or how it's going to be arranged? Where to go? But no, Fridays. So yeah, the last two times I'll see you are Friday and the final, at least in person. Sebastian? No, so your regular classes are done after this week for me and for everything else. So what's that? Friday is the last day of classes. So yeah, next week is Yeah, so I sent the demo in the video here to somebody. If you'd like to hand it in the video, no rush at all. Yeah, so yeah, I kind of expect
Very chance that it's gonna be more on like section or chapter 5. Every time like it.
you should definitely think about 2 sections. So, I mean, I think it's fair to say there'll be some stuff from those 2 sections there.
You know, even like all the chapters.
I tried to make it pretty balanced,
Okay.
with an eye towards stuff that, I mean, there are certainly things we've talked about that we didn't spend a lot of time on that I didn't throw on, really emphasize on homeworks and quizzes. I'll kind of let you decide what those things are, but I would focus less on those and more on the big ideas. So what is a derivative? Can you find a limit? Do you know when limits exist? Do you know when limits exist? Do you know when to find them? Do you know what it means for a function to be differentiable? Clearly, finding derivatives and using them is going to be huge. I mean, that's what probably 3/4 of this class has been about. And then, culminating with integration. We did quite a lot of stuff here, but I would focus on the bigger ideas. So I'll get to you in a second, Jorge. The last thing I wanted to say is, if you go to on Canvas in the modules that exam prep module, like the only thing that's in there right now that wasn't there was awesome practice problems from section 5.3 and section 5.4. Everything else, I don't think you should redo absolutely everything. Take a look and figure out what things you want. I would really hate to show up next Thursday.
They're going to be similar to our previous tests, like difficulty wise. Okay.
That was my intent, but difficulty is a very relative subjective thing. Especially considering I have not taught in person here before, so it's a little bit of a different thing. But if you haven't already filled that out, please take a few minutes and do so. Anything else? All right, I got 12 o'clock. If anybody has any questions about I would strongly encourage you to Friday with ideas and things we're talking about. I'm gonna find some to pass on Friday. See you. Thank you. Yes. I'm sorry. Okay, let me make a note, and then I'll change that whenever I get a chance. Bye. Thank you.
Yeah, so, like all the ones that don't have you can go ahead, something. So I have a question about yeah. Okay, cool. And then so this one. So this one, I was wondering how like yeah, so I don't give you a lot of feedback story. So just wondering, each response here is so you said there's something. Yeah. Let's check that out. Okay, so CV. So it says 22,000 numbers, and so this is yeah, that's fine. So would it be both the that's I just want to make sure this one's like so I wanted so yeah, you gave me the extra coordinates of what I mean, I think I probably made this thing. Yeah, really right. I'm not issues and all these. I mean, that's so. I'm not really sure where I'm going on. This is the and I saw the yeah. And square. Why don't you first? Oh, goes inside the internet camera. Okay.
Could be able to do it the same way.
Or so.
So I don't know why.
A little bit different from our notes. How we set it up would be, verbal, so we set up the
So you got numbers for all three. What is this one? Border cross. So let's try. So you're. So. You're getting very easy. You're doing a three from the. So you need to take the arrow as is. Or you can integrate the gas also. B squared minus 16 plus B. They're both. But one thing that
yeah.
So your displacement is already more than so basically you're telling me this. Here's where I started.
Yeah.
So you're sitting here. Negative 66.
Yeah, that's, 0.66 would be.
You said it was negative 66. You're all telling me he only travels 65. So why is well, we can done these correctly, but you didn't account for the fact it's not okay.
Like the ones that are.
But and then look at this one. Yeah, distance and displacement. Distance is a what's called a scalar.
Yeah.
Okay, so distance only grows in magnitude. Like if you walk backwards, you're increasing your distance. You're losing displacement.
Yeah.
I'll teach you calc one next semester. I just found so I mean, I just found that out last night.
Okay.
Yeah. They don't tell us. I don't find out what I'm teaching until long after you should have registered. So it doesn't really help anybody. But yeah, I got.
That's a good question, actually. I forget.
It might not be. So Joelle Park is she's an admin assistant.
Yes.
So basically all the classes that haven't been assigned yet are just given to her until she gives them away. So yeah, they don't have to teach you that class yet, but they will soon. But, and I'll send out an email to everybody, but yeah, if you need anything, yeah, just let me know. Even though our paths may not cross in class again, but I'm around. I'll be here until after most of you graduate. Yeah, of course. Yeah, of course. Hey, thank you.
Have a great day.
You too. See you Friday.
My schedule got so.
By what?
Take your schedule. And then we'll check over it next week. So I did that. Look at the roll. Let's see how we-
Oh no.
So how we apply everything.
Well, it's saved, but they can still fill up. So how many classes did you get kept out of?
And not just scratch, I just barely classes. And